Hi, and welcome back to our discussion on limits. Right now, we're going to go through some examples to kind of apply what we learned in the last video of just a general overview of limits. If you missed that, definitely go check it out if you just like some basic information on what a limit is. So first, we're going to start with finding a limit graphically. So I can find a limit both graphically and algebraically. So here we're going to go through graphically. I got this little graph over here to the left. Shout out Desmos. So we're going to use that to find it. Again, we discussed I can find a limit from the left or the right. So this little minus here, how I will read this, is the limit as x approaches 0 from the left of f of x. So what I'm going to do is that this graph is of f of x. If I'm coming from the left, cruising down from the left here, as x gets really close to 0, what is y? So as x gets really close to 0, y here coming from the left is 1. So I'm going to go ahead and write 1 there. Now I want it coming from the other side. So now I'm coming from the right. As x is getting really close to 0, what is y? Coming from the right-handed direction, right? So when I'm coming from the right there, y is getting really close to 0.5 or 1/2, if you will. So the limit as x approaches 0 from the right is going to be 1/2. So now I want the limit as x approaches 0. So notice that we don't have a plus or minus here. So I just want the limit as is. From the last video, if you remember, our big deal alert theorem was for the limit to exist, they have to be equal from the left and the right. So the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. Correct? Because I got 1 here and 1/2 here. Not the same. So that means this limit, unfortunately, does not exist. I'm going to say DNE does not exist. The limit does not exist. We'll talk a little more about this in our discussion of continuity, maybe in a couple videos. But even if the limit doesn't exist, this value could exist, right? So this is wanting f of 0. I'm no longer taking a limit. I'm throwing it back to algebra. And I want to say, what is f of 0? So essentially, what is y when x is 0? If we look really close to this teeny tiny baby graph, I can see that this one is bubbled in, right? So when it's open, that means it's not included. When it's bubbled in, that means it is included. So at this value, there's a piecewise function, but at this value, the function does exist. So when x is 0, y is 1. So here, I'm going to say that f of 0 is equal to 1. Last but not least, we're just looking at the limit as x approaches 2. So I'm essentially saying as x gets really close to 2, what is y? And it looks like y there is 4.5. So I'm going to say 4.5. And hopefully that makes sense with the graphing. Another type of question we'll get a lot with limits is asking us to find limits when we're not actually given the function. We're just giving a little bit of information about the function. And this is really going to test our knowledge of our limit laws. So I'm going to go ahead and pop in the limit laws here so we can take a look at them while we solve these. Okay, so there are my limit laws right there off to the side, just in case I need them, and what information is given in the problem. So I'm given the limit as x approaches 1 of f of x is 3. I'm also given the limit as x approaches 1 of g of x is -5. So now we're going to find the following limits using that information and using our limit laws over to the right. So first I have the limit is x approaches 1 of the quantity 2 times f of x minus g of x. So again, like we talked about before, I can break this apart, right? So I can break it apart using this limit law. So I'm going to go ahead and rewrite it like that. So I have the limit is x approaches 1 of 2 times f of x minus, I'm doing these individually, so now the limit is x approaches 1 of g of x. Great. So one last step to get them into this form, right? I'm always trying to get it into the form that I know, right? So I'm always trying to get what information I have, leverage it to help me out with what I'm given. So one last thing I'm going to do here is go ahead and pull out the constant, right? So that limit law there tells me no problem. You got a constant. Just go ahead and chuck it out in front. So now I have 2 times the limit as x approaches 1 of f of x minus the limit as x approaches 1 of g of x. Now everything pretty much looks like what I have, which is awesome. So we're just gonna plug and chug. So this chunk here is the same as this chunk up here. And we got that this chunk here is the same as this chunk up here. So I'm gonna go ahead and plug in those numbers. I got 2 times 3 minus -5, and that is going to be my limit. So this is where they came from. 2 times 3, I got 6, minus becomes plus, and this limit equals 11. Awesome. Moving along to B. So again, like we talked about before, I can break up the quotient and do each limit individually. So I'm going to do 2 steps in one. We went a little slower on the last one. We're going to pick up the pace. I'm going to use this limit law and this limit law. All right. So first I got the limit as x approaches 1, trying to write nice and tiny so we fit in this little baby space, over, pulling out the constant, right? 4 times the limit is x approaches 1 of g of x. So again, this limit of f of x is provided up there, the limit of g of x provided up there. So I got that this will equal 3 divided by 4 times -5. Just throwing in our colors to remind ourselves where everybody came from. So then I got 3 over -20. And that's my final answer. Okie doke. So for C, again, we're going to use 2 limit laws here, and I'm going to chunk them together. So first I'm going to use this one here, right? So I can kind of put the limit inside the square root. And then I'm also going to pull out my constant here as well. Okay, so let's set that up. All right, so first I'm going to pull out my square root. I'm going to pull out my 3. I got the limit as x approaches 1 of f of x. This piece here was 3. Now I have the square root of 3 times 3, which is the square root of 9, which is just 3. Perfect. Last one like this. So I'm going to use this limit law here where I can kind of pull out that square. So I got the limit as x approaches 1 of f of x, and then I'm going to square that whole thing there. This again is just 3. So now I got 3 squared, which is 9 for that limit. Awesome. So I hope that chunk there made sense. Now we'll move into a few examples using the direct substitution property. So like we discussed before, all I'm going to do is sub in this 2 for x, and I can solve using the direct substitution property. So I got 3 instead of x, 2 squared, plus 2 instead of x, I got my 2 minus 1. This 2 is coming from down there. All right, so then I got 3 times 4 plus 4 minus 1, which will give me 12 plus 3. So this limit is just 15. Always underestimate how large my handwriting is. Once again, we're going to try to solve this using our direct substitution property. So just plugging in 0 for x. So I got 2 times 0 plus 1 over 0 squared plus 2 times 0 plus 4, all under a radical. I'm using that limit law as well. All right, so I got square root of 1 over 4. With a radical of a fraction, I could just take each of them individually. So it'd be like square root of 1 over square root of 4, which of course is just 1/2. Awesome. So this can sometimes happen with our limits. Like we talked about before, direct substitution doesn't always work, unfortunately. It is the nicest, most friendliest way to evaluate the limits, but it's not always working for us. So with something like this, if I try to do direct substitution, what's going to happen is I'm going to get 1 plus 2 minus 3, which is 0, over 1 minus 3 plus 2, which is 0. 0 over 0 is an indeterminate form, which means more work to do. When I see a polynomial like this, my first thought is, can I factor it? So we're going to check, can we factor it? Typically your path of least resistance with one of these until we learn L'Hopital, which not until derivatives. So I am going to go ahead and factor. So I have here, the top will be x plus 3, x minus 1. On the bottom, I got x minus 1 and x minus 2. All right, so here comes the fun part. We get to cancel out, right? Since they're multiplied, we can cancel. This cancels here. Now I'm left with the limit as x approaches 1 of x plus 3 over x minus 2. Now I can go ahead and try direct substitution again. So I'm going to do that. So this limit will be 1 plus 3 over 1 minus 2, which will give me 4 over a negative 1, which is just negative 4. Awesome. So we've learned a couple techniques so far with evaluating limits, right? I can use my limit laws, I can use direct substitution, and I can also, when in doubt, do some factoring. So on to the second row of example problems. Deeply regretting picking this many, but here we are. So this one here, if we notice, we cannot use direct substitution. Why? What happens when we do? So if I plug in 2 here using direct substitution, I would get 4 times 2 plus 1 minus 3 over 2 minus 2. 3 minus 3, which is 0, 2 minus 2, which is 0. This is actually an indeterminate form. Can't do that. So sometimes direct substitution doesn't work. Like we said, that's a no-go. We're going to try a different approach. 9 times out of 10, when I have a radical like this, what I want to do is multiply by the conjugate, right? Quick, easy way to get rid of them. Easy, debatable, but quick-ish. So I am going to do that now. So f of x plus 1, the conjugate here, instead of a minus, switch it to a plus. If I do it on the top, I got to do it on the bottom, right? Essentially, all this is multiplying by a fancy form of 1. It's the same on top, same on the bottom. It'll act just like 1, will not change the problem for us. So let's go ahead and do that. First, I'm going to rewrite the limit. I still haven't taken a limit, so I got to keep rewriting that until I actually take the limit. And I am going to multiply this out. So essentially, we're foiling it. So first, multiply those together for x plus 1. Then I got outer plus 3, 4x plus 1, inner minus 3. And then last, 3 and negative 3 will give me a negative 9. I think on the bottom, I am going to leave it like this for now. We'll see if I regret that, but right now, I think I'm going to leave it. Again, I have not taken a limit yet. So still, limit is x approaches 2. Up top, these two actually cancel, right? I got a plus 3 and a minus 3. And then I'll go ahead and combine my plus 1 and my minus 9. So then I got left on top 4x minus 8. All right, so leaving the bottom untouched, I'm going to factor the top, leave the bottom again, and now comes the fun part. All right, so these guys here will cancel, and what am I left with? Not a lot of space, but I'm also left with the limit. Still haven't taken a limit. Limit is x approaches 2. 4 over square root of 4x plus 1 plus 3. Now we'll do direct substitution. All that work just to do direct substitution all over again. But this time I think it's going to work. So I got 4 over this we know was square root of 9 plus 3 from our previous attempt. And now I got 4 over 6, which I could say is 2/3. Goodness gracious, that was a long one, but we survived. Okay, moving right along. So this one here, once again, I cannot do direct substitution, right? So if I plug in the 0 there, I'll get 1 over 0, which I can't have. So what I'm going to do is I'm going to try to combine these two fractions into 1. Probably that's going to be my best bet. So let's rewrite the limit. Then I got 1 over x here. We're going to multiply him by something. Give me a little space. And then I got 1 over x squared plus x over here. So the common denominator that I'm going to go for is x times x squared plus x, since they don't have anything in common. So this first term needs an x squared plus x. Do it on the top, got to do it on the bottom, right? I'm really just multiplying by some fancy form of 1. And then this second piece just needs an x. Again, do it on the top, got to do it on the bottom. Awesome. So let's go ahead, rewrite our limit. Still haven't taken a limit. And then this first one will become x squared plus x. I'm going to go ahead and combine them into one fraction while I do this. Remember, this is a minus, not a plus. So I got a minus x from that second piece, all over x times x squared plus x. So let's go ahead and clean this up. I got a plus an x and a minus x. So that's nice. Those will go ahead and cancel. All right, so I canceled those on top. I am going to also factor out an x on the bottom. So I got an x squared on top left. On the bottom, out of this term, I can take out an x. So this x will become an x squared. And then I'm left with x plus 1. So now I can cancel those guys by. All right, and what are we left with? Once again, no space. Limit is x approaches 0 of 1 over x plus 1. Again, now I'm ready. All that work just to be able to do direct substitution. So now I can plug in that 0. I get 1 over 0 plus 1, which is 1 over 1, which is just 1. Wow, survived another one. All right. Let's keep it going. Now we're going to do some trig limits. So we did have some examples of special trig limits that I might want to memorize in the last video. So those could be helpful here, but generally I try direct substitution first. So first we'll try direct substitution. If that doesn't work, we'll take a look at some of the limit properties that we memorized last time. All right, so plugging it in for direct substitution, I would have cosine of pi over 4 minus a half over sine of pi over 4. Cosine of pi over 4 happens to be root 2 over 2 minus a half over root 2 over 2. All right, we're going to clean this up. On the top, root 2 minus 1 all over 2. Division is just multiplication by the reciprocal, right? So instead of dividing, I'm going to multiply by the reciprocal. So multiplying by the reciprocal. That kind of worked out for us because these 2's are going to cancel. I am left with root 2 minus 1 over root 2. Could I leave this as my final answer? Sure, why not? I am going to rationalize just in case. So some teachers will not let you leave a square root on the bottom and will ask you to rationalize the denominator. So I'll just go ahead and real quick show you how to do that. So I'm going to multiply by root 2 on top and root 2 on the bottom. Why? So I'm going to multiply by this radical in order to get rid of it. If I do it on the bottom, I have to do it on the top. So essentially just multiplying by a fancy form of 1. So then when I go ahead and do that on top, root 2 times root 2 is just 2 minus 1 times root 2, root 2. Root 2 times root 2 is 2. So then this is my final answer. Okay, so for this next one, once again, direct substitution will not work, right? Sine of 0 is 0 over 0. So 0 over 0, indeterminate form, can't do it, right? But I do have over here some of our fancy trig limits that we have from last time, right? That we might want to memorize. And I'm specifically going to use this one here, right? I can do a video on where this is derived. It's kind of a lot of work. So literally I will only do it if it's requested. But for now, you can just take my word for it, right? That this is a limit that I can use. And so in this instance, A is 4 and B is 2. So this limit will just be 4 over 2. Really nice and easy if I have them memorized, right? And that's just 2. This one here, what I want to do a lot of the time is if I don't know how to take a certain limit, right? This is once again going to be 0 over 0 indeterminate form. If I don't know what I'm doing with a certain limit, I do want to try to manipulate it to put it in the form of something I do know how to do, right? So my goal, if I don't know how to do this limit, is to try to make it look like one of these limits using my limit properties and a little bit of algebra. First, I think I will break apart tan. So tan is just sine over cosine, right? So I'm going to have sine x over cosine x. Let's move them up a little bit. Room is always a finite resource. And then minus sine x over x cosine x. Once again, I'm trying to make it look like one of these. So here on the top, I can factor out a sine x. So if I pull out sine x, right here, I'm left with 1 over cosine, which is just secant. So I have sine x times secant x minus 1. Have not done anything to the bottom yet, no big deal. Now I'm going to break it apart. So I want to keep these guys together, and I want to keep these guys together. So I'm going to go ahead and break that apart. This is one of the limit laws we talked about before. So this is going to be the limit as x approaches 0, still haven't taken my limit, of sine x over x times the limit as x approaches 0 of secant x minus 1 over cosine x, right? Just pulling that apart because it's multiplication. So this is one of our special limits. We did it. We got this one in a form we understand. So that's just going to be 1 there, right? And I'm going to multiply by this one. This I can move around a little bit. Let us multiply top and bottom by cosine. So if I multiply on the top, got to do it on the bottom. We're just, once again, multiplying by a fancy formula 1. Doing that a lot today, right? It's a good trick to have in your back pocket. So I took that limit already. It's just 1. I'm still taking a limit here as x approaches 0. So if I multiply the cosine in, secant's 1 over cosine. So now I have cosine over cosine there, which is just 1 minus cosine x over cosine squared x. And let's try a little direct substitution. I got a 1 here. And if I plug in there, I have 1 cosine of 0 is 1 over 1, which is just 1 times 0 and 0. Wow, all that work for 0. All right, by some literal miracle, we have made it to the last one. I'm as relieved as you are. This is a lot of limits. All right, so for this one here, once again, my game plan, this is going to be 0 over 0, indeterminate form. So I want to make it look like one of these. If I don't know what to do with him, I know what to do with these. Going to try to make it look like that. So first I've noticed that I can factor on the top. So let's try that. I'm going to take out a 2, and I'm left with 1 minus cosine x over 3x. From our limit laws, we remember that we can pull out a constant, right? So I'm going to go ahead and do that. I got 2/3 out in front, and then the limit as x approaches 0 of 1 minus cosine x over x. Wow, we did it. I know that one. That's going to be 0. So I have 2/3 times 0, which happens to be 0 again. If you made it this far, thank you so much. This was a lot. I'm tired. You're probably tired. We went through a ton of limits. I really hope that was helpful. If you would like specific types of problems, specific topics, please be sure to comment that. I'd be happy to take suggestions. I also offer private one-on-one tutoring. If you feel like you need a bit more support, please feel free to reach out. Thank you so much for watching, and I'll see you in the next one.